In today's global marketplace, producing a high-quality, in-demand product requires more than just efficient assembly. It demands a carefully selected network of suppliers and manufacturing partners that add real value. For many companies, that search naturally extends across international borders. My name is Catherine Rose, and thank you for joining me. In this presentation, I'll be exploring the Polaris Industries case study, examining the strategic decision the company faces. Should Polaris invest in building a new manufacturing facility overseas or continue production in the existing US-based operations? I'll evaluate the economic, operational, and qualitative factors driving this high-stakes choice. Polaris is a prominent American manufacturer in power sports industry, known for producing snowmobiles, ATVs, UTVs, motorcycles, and boats. Headquartered in Medina, Minnesota, this company has built a strong reputation for innovation, high-performance products, and a brand identity rooted in adventure and durability. Polaris operates an extensive distribution network with over 1,500 distributors in the United States and approximately 1,000 internationally. A core aspect of the company's identity is its commitment to domestic manufacturing. Its vehicles are designed, engineered, and assembled in the U.S., with a substantial portion of components sourced from American suppliers. While some parts and production activities are outsourced globally, a large share of manufacturing continues to be concentrated in the Midwest, particularly in Minnesota and Wisconsin. As previously noted, Polaris utilizes a manufacturing strategy that combines both insourcing and outsourcing. The company outsources the majority of its component manufacturing while keeping final assembly in-house. This approach is driven primarily by cost efficiency, but it also supports Polaris's strategic commitment to maintaining its identity as an American manufacturer. Outsourcing allows Polaris to take advantage of lower labor costs and tap into the technical expertise available in countries such as South America and Asia, regions where a skilled manufacturing workforce is more readily accessible. This is particularly important given the company's concerns about the domestic shortage of experienced technical workers, as highlighted by senior leadership. Conversely, by insourcing final assembly within the United States, Polaris benefits from close coordination between product development teams and manufacturing operations. This proximity enhances communication, accelerates problem solving, and supports product quality. Additionally, maintaining final assembly domestically reduces transportation costs to core U.S. markets, further reinforcing the strategic logic behind this dual approach. In 2010, Polaris was performing strongly both strategically and financially, with a well-established market presence and growing sales. Emerging international markets presented new opportunities for overseas expansion. At this juncture, Sunesh Krishna faced a critical decision, whether to expand manufacturing operations abroad by establishing a new facility or to maintain production within the existing U.S.-based plants. This economic downturn in the United States had exerted significant pressure on Polaris's profit margins, prompting consideration of lower-cost manufacturing alternatives. The primary options under evaluation were to continue production domestically or to invest in a new plant either in China or Mexico. In the following slides, I will present a detailed cost analysis to identify the manufacturing location that offers the most substantial cost savings. But first, Polaris's decision to potentially move manufacturing operations overseas can be evaluated through the lens of vertical integration. By maintaining production within its existing U.S. facilities, Polaris retains direct control over key stages of the supply chain, ensuring tight oversight of quality, production schedules, and supply continuity. However, expanding manufacturing to lower-cost countries such as China or Mexico could introduce complexities in supply chain control, potentially increasing reliance on external suppliers or partners and reducing vertical integration. Conversely, if Polaris opts to build and fully own a new overseas facility, it could preserve a degree of vertical integration by controlling production processes and mitigating risks associated with outsourcing. This approach would allow Polaris to leverage costs in labor and materials while maintaining strategic control over manufacturing quality and timelines. Ultimately, the company must weigh the benefits of cost reduction abroad against the potential trade-offs in supply chain control and integration, as these factors will impact operational efficiency, product quality, and responsiveness to market demands. One example of a company that operates as a vertically integrated company is IKEA. IKEA exemplifies a vertically integrated company by owning and controlling multiple stages of its production and supply chain, from raw material sourcing to manufacturing and distribution. For instance, IKEA owns forests in countries such as Romania and the United States, sourcing a reliable timber supply while maintaining strict control over quality and costs of its primary raw material. Additionally, IKEA operates its own manufacturing subsidiaries, enabling optimization of production processes, consistent quality assurance, and reducing dependency on external suppliers. This company's warehouse and retail network is strategically designed to minimize handling and transportation costs, leveraging innovations like flat pack furniture to reduce shipping volume and associated expenses. This integrated approach streamlines inventory management and distribution. Ultimately, by controlling the key stages of the supply chain, IKEA realizes substantial cost efficiencies that translate into affordable pricing for customers. All right, now on to my quantitative analysis. Since this analysis compares the US, Mexico, and China, the first critical step is to establish accurate exchange rates for the Mexican peso and Chinese yuan. Without these exchange rates, it's impossible to consistently compare production, labor, and transportation costs, as each country operates with different currencies. To determine the 2011 exchange rates, I used historical data provided and applied a linear regression to forecast future values. This is an appropriate method given the clear linear trend in the past exchange rate. In this model, the year serves as the independent variable, x, and the exchange rate as the dependent variable, y. I used Excel's formula forecast.linear, parentheses x, comma, known y's, comma, known x's, to perform the calculation. The result was the Chinese yuan at 6.21 and the Mexican peso at 13.41. These forecasted exchange rates provide the foundation for converting local costs into US dollars, allowing for a fair and accurate comparison of total operating expenses across all three countries. When determining the most cost-effective manufacturing locations, one of the first components to assess is production costs. While in the U.S. production cost is already stated in U.S. dollars at $400 per unit, the costs for Mexico and China are given in local currencies, so I first converted them using the applicable exchange rates. To do this, I divided the local currency unit by the corresponding exchange rate. So for Mexico, 4,560 Mexican pesos divided by 13.41 is $339.94 per unit. For China, 1,950 Chinese yuan divided by 6.21 equals $314.21 per unit. With all the costs now in US dollars, I calculated the total annual production cost by multiplying each unit cost by the annual demand of 14,500 units. The United States, 14,500 times $400 is 5.8 million. For Mexico, I got 4.9 million. And for China, 4.5 million. From this analysis, it's clear that the U.S. has the highest production costs, while China offers the lowest, with Mexico positioned in between. This provides an important baseline for comparing total operational costs across all areas. The next major cost to evaluate is labor across each manufacturing location. For Mexico and China, labor data was only available through 2008, so I needed to forecast wages through 2015. To do this, I used linear regression to estimate annual wage growth rates, applying the same Excel formula as previous. I anticipated that China's wage growth would accelerate due to its rapid GDP growth, which has increased job creation and demand for labor, thereby driving up wages. In contrast, Mexico's wage growth has been slowing, largely due to persistent income inequality and labor costs rising faster than productivity in several industries. To calculate the total labor cost, I used the following formula for each year. Total labor cost equals the number of employees times monthly wage times 12 divided by the exchange rate. This gave me the labor costs for Mexico and China converted to US dollars. For the US, I used the provided wage of $26 an hour and assumed an average of 2,080 hours worked per year, which resulted in an annual wage of $54,080 and a monthly wage of $4,506.67. I then applied a 2% annual wage inflation rate based on historical averages from the Bureau of Labor Statistics to forecast wages through 2015. After completing this analysis, it became clear that the U.S. labor costs are significantly higher by several $million compared to China and Mexico. Interestingly, while China had the lowest production costs, Mexico emerged as the lowest cost option for labor. The next major cost factor to evaluate is transportation. Using the data provided in the case study, I began by calculating the number of trucks needed for road shipments from each location. This was done by dividing the unit demand at each distribution center by the truck capacity of 26 units per truck and rounding up since partial trucks are not feasible. For each U.S. and Mexican facility, I then calculated transportation costs by multiplying the number of trucks by the mileage from each distribution center to the manufacturing facility, timesing it by the mileage rate to give me the total cost. For China, the transportation cost is calculated differently since this goes as a sea shipment. Based on the flat rate per unit of $190, so total cost would equal the demand for that location times $190. So for the Tacoma, Washington location, a demand of 3,650 units for 26 units per shipment is 141 trucks. For the U.S. location, that's 141 trucks times 1,636 miles times $2.30 mileage rate is equal to $530,555. To the Mexico location, that's 141 trucks times 2,261 miles times $2.30 mileage equal to $733,242. For the Los Angeles location of 7,050 units, the trucks needed is 272 trucks. That's 272 trucks times 2,161 miles times $2.30 for the U.S. location, coming out to $1.3 million. For the Monterey location, that's 272 trucks times 1,505 miles times $2.30 mileage, which equals $941,000. To the Irvine, Texas location, that's 3,800 units. That's 147 trucks times 1,267 miles times $2.30 mileage equals $428,000. From the Monterey location, that's 147 trucks times 437 miles times $2.30, $147,000. So the total transportation cost for the Russo location in the U.S. is $2.3 million. For the Monterey location in Mexico, it's $1.8 million. And then for China, it's $2.7 million. So assuming demand remains consistent, the U.S. transportation costs are going to be $2.3 million, the Mexico transportation costs $1.8 million, and the China transportation costs of $2.7 million. These figures highlight the transportation cost advantage of manufacturing in Mexico. Now, since I have not previously factored in tariffs on imports from China, I now incorporated them into the analysis. To calculate the total tariff costs, I added China's production and transportation costs, then applied the current tariff rate. Assuming no changes to these underlying costs, the estimated tariff burden amounts to $365,000. This additional cost further narrows the gap between China and Mexico. Finally, by reviewing all the financial data, I was able to draw a clear conclusion. Using net present value to account for the changing cost of money between 2011 and 2015, the total projected costs are approximately $43 million for the U.S., $26 million for Mexico, and $31 million for China. Based on this bottom line, Polaris would realize a cost savings of $16 million by shifting operations to Mexico and $12 million by moving to China. These results clearly indicate that Mexico is the most cost-effective manufacturing option. While Mexico had the second highest production costs, it benefits from the lowest labor and transportation costs, which more than offset the difference. To further illustrate this, I calculated the savings per unit by dividing the $16 million in total savings by the projected 5-year demand. The result, a savings of $5,749 per unit, a substantial reduction that could be passed along to the customer. This is especially significant given that Polaris side-by-sides retail between $10,000 and $15,000 for a mid-size model, making this cost advantage a compelling opportunity for competitive pricing and margin expansion. To validate my conclusion, I conducted a sensitivity analysis to examine how changes in key input variables affected the model's output. By systematically adjusting variables such as annual demand and tariff rates on Chinese and Mexican imports, I was able to assess the robustness of the recommendation under different scenarios. For example, when I increased demand by 500 units each year, the net present cost rose by approximately $1 million across all locations, and a savings per unit increased around $70. However, with these adjustments, Mexico remained the most cost-effective option, reinforcing the strength of the initial recommendation. Next, I explored how increasing tariffs on imports from China and adding tariffs from Mexico would impact the overall cost comparison. Starting with my original input values prior to adjusting for the increased demand, I created a table to project the net present value for each country under a scenario where tariffs rise incrementally each year. To model this, I created random tariff rates and calculated total tariff costs for each country. As expected, higher tariff rates led to a corresponding rise in total tariff costs. Specifically, the net present value for China increased to $32.4 million, an increase of roughly $1.4 million, and Mexico increased to $29.6 million, an increase of $2.2 million. Cost savings also dropped for both countries. Even with this added cost, Mexico remained the most cost-effective option, reinforcing its position as the best strategic choice for Polaris. Finally, several critical qualitative factors must be carefully considered. Factors that, while not easily quantified, carry significant long-term strategic, operational, and reputational consequences. These include the political climate, the quality of infrastructure, cultural compatibility, and the potential impact on brand perception. Infrastructure in both Mexico and China varies greatly, particularly in terms of road conditions, facility readiness, and logistic reliability. Polaris has estimated that establishing operations would require upfront capital investment of $10 million in China and $9.5 million in Mexico, a substantial outlay with no guaranteed return. Additionally, the increased exposure to natural disasters in certain regions further elevates the operational risk. In today's volatile global environment, political uncertainty cannot be ignored. The current U.S. administration's strained relationships with both Mexico and China has led to increased diplomatic tension, highlighting the risk of policy shifts, trade restrictions, and tariff hikes. These geopolitical factors could quickly erode any cost savings gained from relocating production abroad. Moreover, cultural differences in labor practices, management expectations, and communication styles could hinder operational efficiency and threaten Polaris's ability to maintain its strong brand reputation for quality and reliability. In light of these risks, the potential rewards of offshoring may not justify the strategic vulnerabilities it introduces. In conclusion, after thoroughly analyzing production, labor, transportation, tariffs, and currency exchange rates, Mexico clearly emerges as the most cost-effective manufacturing location for Polaris. While China offers the lowest raw production costs, its rising labor costs, compounded by tariff risks and geopolitical instability, significantly reduce its overall cost advantage. The U.S. remains the most expensive option across all categories, making it the least competitive from a cost standpoint. Mexico strikes the best balance. It has a slightly higher production cost than China, but it's offset by substantially lower labor and transportation costs. The currency forecast also shows stability, giving Polaris greater confidence in long-term planning. Based on this comprehensive analysis, I recommend that Polaris move forward with establishing a manufacturing facility in Mexico, as it provides the best opportunity for cost savings while maintaining operational flexibility and reducing strategic risks. Thank you.